Hey friends, welcome back. We've got this problem. We want to find the end behavior for this function. So the phrase end behavior refers to what happens as the x value becomes very large or very negative. So sort of in the context of a graph, right? Let's take a look here. I've entered the f of x function in y1, and I'm going to click graph. And so, as we can see, as x gets really big, so as we're going far to the right, it looks like the y values are going to approach some number. And similarly, as we go to the very left, so as x becomes super negative, the y values are approaching some number. Now, those two numbers might not be the same. So we can have a right end behavior and a left end behavior, but nevertheless, the phrase end behavior refers to what happens to the y values as x becomes really big going out toward the right or really negative going out toward the left. Now, you might remember from algebra precalculus that we refer to this behavior as a horizontal asymptote. And our goal is to understand sort of how to apply calculus to this to get that similar analysis. All right, so first things first, conceptually speaking, if we look at this, we got x cubed, x squared, and then a number 39. And so what we're going to do is we're going to make x very large. And so in the calculus sense, this is actually how we're going to write it. We're going to write the limit of f of x as x approaches infinity. So a little bit strange, because in the past, when we wrote this limit, I said something like x is going to get very close to whatever number shows up here, but x is not going to be equal to that number, which raises the question, is infinity a number? And the answer is no. Infinity is not a number. Infinity is a symbol we associate with this concept that no matter what number you pick, I'm going to be bigger than that, right? So if I pick a million, we can be bigger than a million. If I pick a billion, we can be bigger than a billion, and so on and so on. So this is saying as x becomes bigger than any number you can possibly choose, meaning you're going very far out to the right indefinitely. The question is going to be what happens to the y values. Okay, so conceptually speaking, we're going to look at this and say, well, imagine if x is a huge number. So like even a million, right? What is a million squared? Well, that's a million times a million, which is a trillion. That is a huge number, right? So compare 14 trillion to the number 39. Well, imagine if you had $14 trillion. Would you stop to pick up $39 on the side of the road? The answer is probably not. You have $14 trillion. So conceptually speaking, once x gets very large, the number 39 just doesn't matter compared to how big 14x squared is. Okay. Same logic if I look at x cubed. Well, x cubed is x times x times x. So if x is a million, then this is a million times a million times a million, which is a million times as big as this thing. So compare 5x cubed to 14x squared. This is, right, like think about it as 5 million compared to just 14. That's effectively the comparison we're making. And so the argument is, when x becomes a super large number, you only really care about the biggest power of x. Everything else is just insignificant compared to the biggest power of x. So if we focus super hard on just the biggest power of x, we get 5x cubed, and then we get 9x cubed on the denominator. Notice the order doesn't matter. I'm just looking at the biggest power of x. And once all that's said and done, and we forget about all the rest, 5x cubed over 9x cubed, perhaps you could believe that the answer should be 5/9. Okay? And now we can sort of see this in the graph if I were to go into the y equals and make a simple y equals the number 5/9. This should draw a horizontal line at the value 5/9. If I hit the graph, it looks like that, just eyeballing it, is the y value that this graph is approaching. That's the horizontal asymptote, y equals 5/9. Okay. Now, it's important to note that we did this conceptually, there are going to be sort of two steps of formalizing this process, and I want to do that just in a moment. But before we go there, I was saying something about maybe if we go toward the right, we'll approach a certain y value. Maybe if we go toward the left, we'll approach a different y value, or maybe we'll approach the same y value, right? These are possible behaviors depending on what kind of function you're dealing with. So we write the limit of f of x as x approaches positive infinity, x is becoming a huge positive number, to indicate the right end behavior, and we write the limit of f of x as x approaches negative infinity to indicate that x is becoming a super negative number. Once again, using the symbol infinity to say no matter what negative number you pick, x is going to be more negative than that number you picked. So we're going far out toward the left. Now, once again, since x is going to be negative but a super negative number, think negative a million, negative 1 billion, negative 1 trillion, and more negative, the same idea conceptually applies, where only the biggest power of x really matters for our analysis, and all the smaller powers of x, just they're insignificant compared to the biggest power of x. So we focus on this and say, oh, 5x cubed over 9x cubed should just be 5 over 9. So here, once again, we get 5 over 9. The right end limit and the left end limit are the same number. Okay. So the next sort of step up in formalizing this is say, all right, what I want to do is I want to take this and sort of really say, how am I writing that the smaller powers of x are insignificant compared to the largest power of x? Okay, so this is what I'm going to do. I'm going to factor out the largest power of x here. So I'm going to write this, the limit as x approaches infinity of 5x cubed plus 14x squared plus 39 all over 7 plus 10x plus 9x cubed, okay, and factor out the x cubed from the numerator and the denominator. So that's x cubed, 5 plus 14 over x plus 39 over x cubed all over. X cubed factored out gives me 7 over x cubed plus 10 over x squared plus 9. All right. So far, so good. Then I'm going to make the argument that this x and this x are the same number, right? Like x can be any number. I'm just considering larger and larger numbers for x, but x is still a number. So x cubed on the top and the bottom, I can cancel these, and I will simply have this remaining. Okay. Then I can apply a property of limits that says if the limit of the numerator exists and if the limit of the denominator exists and the bottom limit is not 0, I can split this into the top and the bottom. Okay. Now I can look at each of these and say, well, if the limit of this exists, if the limit of this exists, and if the limit of this exists, then the limit of the sum I can split into the sum of the individual limits. So being overly technical, I'm going to write this all out. And of course, in the future, we won't write all of these steps. It's fairly accepted that you can skip many of these. The limit as x approaches infinity. And really my goal here is just for us to appreciate that we're doing this using the building blocks that we've been quietly building in the background, / I've been using Trust Me Bro to claim that they are valid. Okay. So we've got this. Now, no matter what x is, 5 is just 5. So the limit of this function 5 as x approaches any number is just the number 5. Okay. This is going to be 5 here. Plus, now here's the deal. As x becomes a very big number, 14 divided by a big number. So let's just go back to the home screen in the calculator and think about this together. What if I take 14 and I divide it by like 10,000? 1, 2, 3, 4 zeros. Oh, one more zero. And hit enter. That's 0.0014. That's a fairly small number. Now, what if this x on the denominator gets even bigger? So let's say 14 divided by a million. 1, 2, 3. Okay, that's 6 zeros. Hit the button. 1.4 times 10 to the minus 5. That's 0.00014. It's even smaller than what we had before. So we can see quickly that as this denominator becomes a bigger number, as x becomes a bigger number, then this quotient should become a smaller and smaller positive number approaching 0. And it turns out that anytime you have an x in the denominator where the power of x in the denominator is more than the power of x in the numerator. So in this case, there's no power of x in the numerator, and there's an x to the 1 power in the denominator. That limit is going to be 0 as x approaches infinity. Similarly here, the power of x in the denominator is bigger. I'm going to have 0. Here, the power of x in the denominator is bigger, so I get 0. Power of x in the denominator is bigger, so I get 0. And then 9 is just a number 9, no matter what. So it doesn't matter what x approaches, I'm simply going to have 9 here. And after all of that, I get 5/9 in agreement with our conceptual argument that only the biggest power of x should matter on the numerator and denominator, which gives us a limit that matches the horizontal asymptote that we observed when we graphed this. So before we move on, let's do another quick example of a similar thing and discuss how we want to show our work, assuming this is, a quiz or a test. Okay, so here the phrase end behavior does not show up. It simply says evaluate this limit, the limit of this function as x approaches negative infinity. So we understand x is going to become a very negative number. So on the graph, we're going to go far out toward the left. Okay. And we already understand that when x becomes a very negative number, so it's negative, but the number part of it, the absolute value of it, is going to be huge. So only the biggest power on the top and the biggest power on the bottom should really have any effect. Okay, so let's show our work the way we would on a test. We're going to rewrite this limit, and you have to keep rewriting this until you actually resolve the limit by letting x go to this very negative number. In the meantime, when we're processing and simplifying things, we have to keep writing this limit, okay? And I'm going to factor out the largest power in the numerator and in the denominator. So in the numerator, the largest power of x is going to be just x. So here we have x, and we're going to have 1 minus 9 over x, okay? And then on the denominator, the largest power of x is x squared. So we're going to factor that out and say this is x squared. This is going to be 9 over x squared plus 2. Okay, then we look at this x and this x squared and say, well, x is a number, and it's not 0 because it's going to be deeply negative. So whatever x is, I can simplify by dividing the top and bottom by 1 power of x. So from here, I can look at this and go, can't I rewrite this in the following way by saying this is the limit as x approaches negative infinity of this is 1 over x multiplied by the limit as x approaches negative infinity of 1 minus 9 over x like so. So if this limit exists and this limit exists, then we can say the product of these limits is going to be the limit of the product. Right? And the reason I'm saying this is if I had this x and this x squared, I could rewrite it to actually look like this, where there's no longer a square in the denominator. So I'm simply sort of splitting it along that product and turning it into those two things. Okay? Now, a little bit of a trust me bro moment, but hopefully I was able to at least conceptually justify that when you have a fraction and the power of x in the denominator is bigger than the power of x in the numerator, so there's 0 powers of x in the top, 1 power of x in the bottom, then as I go to a deeply negative number or a massively positive number, right? So when I divide by a billion, a trillion, 1 divided by a large number is basically 0. It gets closer and closer to 0. Similarly, if I divide by like a negative a million, negative a billion, negative a trillion, then 1 divided by that super negative number is going to be negative just a little bit, like negative 0.000001, so and so on. So it's basically 0. So this entire thing, regardless of whether I'm approaching negative infinity or positive infinity, any fraction where the denominator has a bigger power of x is just going to give me 0. So the limit does exist. And over here, I do the same thing, where I'm going to split into the numerator and the denominator, so separate limits, and then I'm going to split into these two things that are added together, these two things that are added together. So in the previous example, I wrote out all that stuff very exhaustively. It's well accepted that you don't have to show all that work. You can just skip here and go, all right, look, this is going to turn into 0 because the denominator here has a bigger power of x. This is going to turn into 0 because the denominator here has a bigger power of x. So you ignore these two pieces and say simply, it's 1 over 2, and the limit here turns into 1/2. So 0 times 1/2. This limit exists, and therefore you can multiply them together and get that the answer is 0. And just to confirm our intuition, if I do y equals, and here's my function, so the x minus 9 over 9 plus 2x squared, I'm going to go ahead and graph this. And we're looking as x approaches negative infinity, so we're going to the far left. X is going to be a super negative number. The y value should approach 0, which it looks like it's doing. That is the horizontal asymptote, y equals 0. So to quickly recap, whenever you get a limit as x approaches either positive infinity or negative infinity, okay, you simply look at the biggest power of x on the numerator and the biggest power of x on the denominator. So in this case, it's x over 2x squared. And I showed sort of the steps algebraically to getting to an answer, but you can actually just say, well, in this case, the denominator has a bigger power of x. So I'm taking a large number, but dividing it by a large number times a large number, right? So imagine x is negative a million. That's negative a million times negative a million, which is 1 trillion. So if you take a million divided by, or I guess negative 1 million, divided by 2 trillion, you get a tiny number, basically 0. Hence, the limit is 0. Okay, one more time. If you have a fraction, and you're taking the limit as x approaches either positive or negative infinity, you look at just the biggest power of x on the top, just the biggest power of x on the bottom, you ignore everything else. And if the denominator has a bigger power of x, the limit's going to be 0. And if it's not, like it was in the previous example, you would simply, so I guess I'll just write this really quick. Let's imagine we were trying to do this, and I changed this to x squared minus 9 over 9 plus 2x squared. Then I would consider just the biggest power of x on the numerator, the biggest power of x on the denominator, ignore everything else, and I would say this is simply going to be 1x squared divided by 2x squared, which should become 1/2. And that's what we expect for the answer. Okay, let's advance the discussion to include some exponential functions. So once again, we're trying to take the limit of this function as x goes to a huge positive number, all the way out toward the right on the graph, and we're trying to find the horizontal asymptote if there is one. Okay, this is the end behavior analysis. So in the previous examples, I tried to convince you conceptually and sort of built a trust me bro moment that the limit of 1 over x as x approaches infinity is 0. Meaning as x becomes a hugely positive number, when you take 1 divided by a hugely positive number, your answer becomes smaller and smaller, close to 0. So we say the limit is the y value 0. And this could be x squared, x cubed. And it turns out we can even have like fractional powers of x. If it's like x to the 1/2 or like x to the 5/7 power, this still comes out to 0, as long as the denominator has a bigger power of x than the numerator. Okay. Once again, totally trust me, bro moment. Now, what I also want to convince you is when you invoke these exponential functions, that the limit of e to the negative x as x approaches infinity is also 0. And let's talk about why this is. All right, so if I quickly go and try to graph this, e to the negative x, I click this graph. So this is the exponential function. So think e to the x. E to the x is a small positive number here, and then whoop, goes up that direction. Switching out e to the x for e to the negative x, right? We're changing the x variable to a negative x. That just flips the graph horizontally, so we get this behavior. Okay. So as x goes to a massively positive number, as we go out toward the right, the y value appears to be approaching 0. Okay. Now, the reasoning for this is e to the negative x is the same thing as 1 over e to the x, right? That's how negative exponents work. So if I imagine as x goes to a hugely positive number, e raised to a hugely positive number, right? E is like a 2.72-ish number. So that number raised to a big positive power is a huge number, right? So that's like saying 1 divided by a huge number is, oh, that's just the same argument here. It should be 0. Right, so this is the conceptual argument that ultimately leads to a trust me bro moment that this is a true statement. Now, if we apply that logic to this problem here, okay, we're looking at this and saying, okay, well, can we split the limit into the numerator and the denominator? As in, can we do this? The limit as x approaches infinity of 16e to the minus x plus 5, boop, boop, all over, limit as x approaches infinity of 5e to the negative x plus 16. As long as the numerator limit exists and the denominator limit exists and the denominator limit is not 0, this is okay. Well, then we can split this into the limit of that thing and the limit of that thing. So I'm not going to write out the whole process of splitting the limit into this limit plus that limit. We're just going to say, all right, the limit of e to the minus x as x approaches infinity is 0. So this part is going to become 0. This part is also going to become 0, which means the only things that are going to be left over are the 5 and the 16. So I can quickly say that my answer is 5 over 16. Kind of like what we did before, where we said anything where you have something divided by x or something divided by x squared, where the power of x is bigger on the denominator, you were able to just call that 0. Based on that property. Now, anytime you have e to the minus x as x approaches infinity, you can remember, right? Why is this? Because e to the minus x is the same thing as 1 over e to the x, and as x goes to a huge positive number, e to the huge positive number is also a huge positive number. Okay, so 1 divided by a huge positive number is very close to 0, so we say the limit is 0. Okay, so we're going to get a little cheeky here. And we're going to do a similar problem, except this time we're going to let x go to a super negative number. So we're looking for the left end behavior, as x goes way far to the left. Now, here's the problem. This logic hinged on if x is a big number, we're dividing by a big number, so we're close to 0. But what if I try to put a negative number into here? A negative of a negative is a positive number, and e to a positive number is going to be potentially very large. Oh, so now we're in a situation where if 16 times e to the negative x, which is 16 times e to a huge positive number now, right, because negative, negative, that number is so big that 5 is going to become insignificant compared to that. We're going to do something similar to what we did with the x's. So formally, once you identify that one piece of the numerator is much larger than the other piece, it makes sense to factor out that sort of large piece. And this is what it's going to look like, okay? So I'm going to factor out e to the minus x. Limit as x approaches negative infinity. Factor out e to the minus x. Now this is going to be 16 plus, okay, 5e to the regular x. Wait, how did that happen? Because factoring is a process of dividing, right? If I factor e to the minus x out, I'm saying here, I'm going to divide this and that by e to the minus x. Oop. So this divided by e to the minus x becomes just 16. But if I take 5 and I divide by e to the minus x, dividing by e to the minus x, right? Think 1 over e to the minus x is the same thing as 1 over e to the x, which is the same thing as just e to the regular x. Okay? That's why this e to the regular x pops up here. That's the division way to think about it. But also keep in mind that when you factor out, you should be able to reverse the process. So if I distribute e to the minus x to here and here, I should get 16e to the minus x, and then 5e to the x times e to the minus x. Remember the way exponent rules work? E to the minus x times e to the x. You get to add these together, which gets you e to the 0, which is simply 1. Right? So this and this e to the x will cancel, leaving me with just 5. Okay, so that's the factoring out process. Same thing on the denominator. We're going to factor out the e to the minus x and make it look like this. 5 plus 16e to the x. Okay? Now we're going to make the argument that x is a deeply negative number. E to the negative number, e to the positive number, is some number, it's not 0. So this is not 0, this is not 0. I can safely cancel these two. Then I can apply my old logic and say, well, what if I just take the limit of the numerator and take the limit of the denominator separately? And if I can show that the limit of the numerator exists, if the limit of the denominator exists, and the limit of the denominator is not equal to 0, then I'm able to do this. Okay. Which then begs the question, what happens if I take the limit of e to the x as x approaches negative infinity? Well, erasing this so it's out of the way, let's think back to here. What if I think of the following? If I put a massively positive number in for x, this is e to the super negative, which is apparently 0. So if x is a super negative number, and I put that in here, that should make e to the super negative, which is literally the same thing as this. Right? In fact, I can just claim a change of variables, and these should be algebraically equivalent. Oh, they are the same thing. I want you to actually pause and think about that and make sure that that makes sense to you. And just from a graph perspective, right? What's the difference between e to the minus x and e to the positive x? If you turn x into negative x, that means flipping the graph horizontally. So we can see that very quickly here. If I just go to a new line and I do e to the regular x and I graph this, the red is going to be e to the regular x. Okay, right? That's horizontally flipped. So in the blue graph, as x approaches all the way to the right, my y value approaches 0. But if I flip it horizontally, then as x goes way to the left, oh, that should be the same analysis. Cool. Hopefully this is a reasonable trust me bro argument. Now we go to here and we say, okay, as x approaches negative infinity, the limit of e to the x is going to be 0, and the limit of e to the x is going to be 0, so what's left over is simply 16 and 5, and my answer here is 16 over 5. Notice it is not the same answer as this up here. Of course, the question then becomes, well, is it just going to be the reciprocal all the time? The answer is also no. This was a sheer coincidence because of the way these numbers came out, right? For example, if I had changed this 16 right here, if I want to turn this into, let's say, 29, where would that change my answers? Would it change this? Yes, right? Because these are the pieces that disappeared, and we only looked at the 5 and the 16. So this would turn into 5 over 29, okay? But now down here, let's imagine I turn this into 29. Well, as I factor out the e to the minus x, the 16 and the 5 are the ones I ended up focusing on, so my answer down here would remain at 16 over 5. So this relationship that we happen to see was purely a coincidence. Don't fool yourself into believing that the limits are always going to be reciprocals of each other. They might not be. Okay, real quick, let's look at the graph, and then we'll go into the rant section of the video. So in the y equal, I have the function, and I didn't put the 29, I'm going to keep the 16 that was there originally. I'm going to hit the graph button. So keeping in mind, the way this limit relates to the graph is we're saying as x goes way out to the right, what is the y value going to approach? We believe the y value should approach 5 over 16. That should be the horizontal asymptote. So let's go y equals and go 5 divided by 16. Boom. And then we'll graph it. That looks like a reasonable horizontal asymptote. The graph is approaching that as we go to the right. But as we go out to the left, the graph is clearly not approaching the same horizontal asymptote. This is what I hinted at in an earlier example, where I said maybe the right end behavior and the left end behavior, sorry, I guess I'm pointing the opposite direction, will be the same. Maybe they will be the same, like they were in the first example with the fractions. In this case, they are clearly not the same, because if I let x go to the far left, then we're going to see here that our y value should approach 16 over 5. Let's do a y equals, go down here and go 16 over 5. Enter end graph. And that, in the black, is the other horizontal asymptote. It is possible for a graph to have two separate horizontal asymptotes, one corresponding to the right end behavior and another one corresponding to the left end behavior. I just wanted you to see that. Hey, we made it to the rant portion of the video. So, in an earlier video when I first started discussing limits, I said that there was a formal definition for a limit, and I also said in that video that we tend not to focus too hard on that at the intro calculus level, and that I wouldn't be focusing too hard on it in these videos, maybe another time, okay? This was that definition. Say the limit of f of x as x approaches a number c is equal to this limit number L if and only if, for any epsilon you pick, I can give you a delta in response so that as long as the difference between x and the number x is approaching is less than the delta I gave you, that means the difference between the y value outputs of f of x and this limit that we're proposing, that difference is less than epsilon. So sort of conceptually what this means is you're able to get closer and closer along the y direction and then designate a sort of horizontal gap that as long as you stay close in this direction, that forces you to stay close to the limit in this direction, meaning you're approaching a value. That's sort of the conceptual way to understand this, okay? But why am I bringing this up now? Is because now we have this idea of the limit as x approaches infinity of f of x. There's the problem. Infinity is not a number. So I can't say that the difference between x and infinity is less than something because infinity is not a number. I can't have a distance to infinity. Okay? And so in math, symbols are super important and we have to respect the meaning of symbols, right? Because we define things very strictly and we build math around these strict definitions. So it turns out, in the context of limits, when we write this statement, it has a technical meaning that's conceptually similar to this, but is technically different. And this is how it goes. We say, okay, the limit of f of x as x approaches infinity is equal to a number L. This is our limit. If and only if, okay, so it maintains that for all epsilon greater than 0, there exists. And you could write the letter delta, totally fine, but we tend to change the letter. We write something like this, capital N greater than 0, such that as long as x is bigger than this number n, the difference between the y value outputs of f of x and the limit L is less than infinity. So, similar structure, but technically different. We're basically saying that we're able to get closer and closer along the y values as long as x remains bigger than this number, right? X is becoming bigger and bigger and bigger. We're going far out to the right. And sort of by a similar token, we can say the limit of f of x as x approaches negative infinity is equal to L if and only if for all epsilon greater than 0 there exists. And there are various ways you can write this. The one I like to write is, once again, n greater than 0, such that the difference here is if x is less than negative n, right? So n is a positive number. X has to be more negative than the negative version of that presumably large n positive number. That this forces this to happen. Okay, so a bunch of symbols, a bunch of me talking. How much of this do you have to understand, internalize, or think about at this stage? And I'm going to go back to my earlier, you don't really have to worry about this for now, right? It's sort of my job to convince you that whenever I say, trust me, bro, that I'm not just lying to you, I'm not just pulling stuff out of thin air. All of the things I've told you are technically provable using these definitions, and the proofs aren't generally that complicated. Okay. But in intro calculus, we tend to not really force students through those proofs. We just say, look, take the trust me bros, use those building blocks, and then solve the problems by putting those building blocks together. I just want to form this trust with you whenever I can to sort of, make sure that what I'm saying resonates a little bit and I'm not just straight up lying to you. Cool? All right. Well, hopefully we learned something. Hopefully that was some fun, and I'll see you guys next time. Peace.